Section 4.8 talks about L'Hopital's rule. And in L'Hopital's rule, we deal with all the exceptions that we ever used before. Now, just to demonstrate really quick, 1 over infinity. So here, this is not really infinity. This is the limit as x approaches infinity. So if I was looking at 1 over x, taking the limit as x approaches infinity, well, 1 over, think of infinity as a massive large number, like a trillion. 1 divided by a trillion is a number very small, that's very close to 0. As x approaches infinity, gets bigger than a trillion, then this fraction approaches 0. Here, think of picking a very small number, say 0.000001. 1 divided by 0.00001 is roughly 100,000. 1 divided by 0. Let's say 9 zeros and a 1 is a billion. So as the limit of x approaches 0, 1 over that will approach infinity. Generally speaking, how we're going to use this, 1 over infinity is 0 and 1 over 0 is infinity. Now, if we add two infinities, if we add two very large numbers, we get a large number. If you have an infinite large number, you add a constant to it that doesn't change it. If you have an infinite small number, not small number close to 0, like negative a trillion, and you add a positive number or subtract a number, it's still infinity. Think of as a very large number. If you multiply it by a constant, if that constant is negative, then a large number times a negative becomes the opposite. And if it's positive, it stays infinity. Those cases are not a problem. These cases are. When I look at infinity minus infinity, we have a problem. When we get infinity times 0, we also have a problem. Again, these are limits. So for example, the limit as if you say x minus x cubed approaches infinity. Well, obviously, this is approaching infinity, this is approaching infinity. Since x cubed is going to reach infinity a lot faster, negative x cubed will dominate. The answer will be negative infinity. If I made this x to the 4th, now this is dominating over x cubed. That's infinity minus infinity. In this case, since x to the 4th is dominating and it's positive, the answer will be positive infinity. And if I made those x to the 4th minus x to the 4th, this is approaching infinity, this is approaching infinity. Well, infinity minus infinity in this case will be 0. So there's no telling of what that would be. Same here. You have a function that's growing to infinity, a function that's growing to 0. Which one is growing faster will dominate. 0 over 0 is the really core of this section, and infinity over infinity is the core of this section. That's something that we deal with all the time. Another 4 undefined terms. If you have 0 raised to the 0 power, we don't know what that is. Infinity to the 0, we don't know what that is. 0 to the infinity, and the most confusing to students, 1 to the infinity is not 1. It's 1 a lot of times, but few times it's not a 1. So you see one of those, you should really be cautious with how to proceed. Now, L'Hopital's rule states, if you take the limit of two functions divided, f of x divided by g of x, and you throw b in, if you get 0 over 0 or infinity over infinity, then this limit will equal, and every time you use L'Hopital, you put an h on the equal the limit as x approaches b of the derivative of the top function divided by the derivative of the bottom function. This is not the quotient rule, and that's L'Hopital's rule. This is probably the most used rule in this class, your next semester, and the 3rd semester calculus. Now, this is for you to keep track of what the limit should be. If you see a factorial is the fastest growing function that we know of. After that in order is exponential, polynomials, radicals, and logs are by far the slowest growing functions. If I'm looking at this problem, for example, I notice there's an exponential divided by a polynomial. Since this ranks higher, the top of this fraction is going to approach infinity faster than the denominator. So I'll know the answer is infinity. You can't use this to justify your answer, but you could use it to figure out what the answer is. So how does limit work? you take the limit as x approaches infinity. Well, e to the x as x approaches infinity exponential growth, that's infinity. Limit as x approaches infinity of x, that's infinity. Well, by L'Hopital's rule, that's the limit as x approaches infinity of derivative of e to the x is e to the x, and derivative of x is 1. And the limit as x approaches infinity of e to the x is infinity. So the first few problems are going to work out just to make sure you know how to practice this. Here, assuming k is bigger than 0. If k is bigger than 0, well, we know logs are the slowest growing function. We know this is going to dominate, and this limit, since the denominator is growing faster than the top, is going to be 0. Well, as x approaches infinity, natural log approaches infinity very slowly, but it's going to get there, and a power function approaches infinity if k is positive. So by L'Hopital's rule, that's the limit as x approaches infinity. I take the derivative of natural log of x, well, that's 1 over x. Take a derivative of a power function, that's kx to the k minus 1. And if I clean that up, that is 1 over k, and you end up multiplying those, and that gives you x to the k minus 1 times x to the 1 is to the k. If k is positive, bigger than 0, that's going to approach infinity, and 1 over infinity we agreed was 0. So this limit right here will be simply 0. I'm going to shift a few things around. All right, again, this is just for practice. This is the majority of what you use it on, but there are a few cases that you're not going to like, but you know, it's all good. You'll get used to it. So what if I want to take the limit as x approaches infinity, as x approaches a of x minus a over x cubed? Well, if I plug x, a is a constant, but it's not 0. If I put an a in there, a minus a is 0, and a cubed minus a cubed is 0. Since I get 0 over 0, I could apply L'Hopital. That's the limit as x approaches a of the derivative of the top. Well, derivative of x is 1, derivative of a is 0. Derivative of the denominator is 3a squared minus 0. 3x squared, forgive me. And if I take the limit as x approaches a, don't you plug a in and you get 1 over 3a squared? So this dominates over most of what we did in chapter 2. And you might be wondering, how come I didn't teach you that from the beginning? Because this requires derivative, and we learned limits before we learned derivatives. Actually, the definition of derivative requires a limit. How about here? If you put 0 in, e to the 0 is 1 minus 1, that's 0 over 0. I could use L'Hopital. Limit as x approaches 0. Derivative of the top is e to the x. Derivative of the denominator is 1. And that will be e to the 0, which is 1. Now, this is emphasizing that the only time you could use L'Hopital if you have 0 over 0 or infinity over infinity. So the next two examples have that. But after that, things don't match. You have to force them to match. If I throw 1 in, 1 minus 1 is 0. If I put 1 in there, oh, this one is a tricky problem. That's 0 over 1 minus a negative 1. That's 0 over 2, which is 0. Again, L'Hopital doesn't apply. Here, pi over 2. Cosine of pi over 2 is 0. Pi over 2 minus pi over 2 is 0. By L'Hopital, that's the limit as x approaches pi over 2. Derivative of cosine is negative the sine of x. And derivative of the denominator is negative 1. And if you throw that in, that's the sine of pi over 2, which is a 1. Now comes the part when things don't match. Well, if it doesn't match, then what you do, so this is the case of you getting 0 times infinity. 0 times infinity, you can't use L'Hopital. To use L'Hopital, it has to be infinity over infinity or 0 over 0. Recall that if I have, I'm showing you this, if I have f divided by 1 over g, that will be f times g over 1. Instead of dividing, you multiply by the reciprocal. And if I have g divided by 1 over f, that will be g times f over 1. So if I have f times g and I'm having 0 times infinity, I can write that as either f divided by 1 over g or g divided by 1 over f. By doing that, you force, instead of 0 over infinity, you're kind of saying I'm going to make it 0 divided by 1 over infinity, which is 0 over 0, or you're saying it's infinity divided by 1 over 0, which is infinity over infinity. Now, of course, you can't play with infinities, but you could play with the limit as x approaches infinity. In this case, if I take the limit as x approaches infinity, square root will approach infinity, and e to the negative x as x approaches infinity, that's a 0. In this case, I could manipulate algebraically and say, well, simple fix e to the negative x, I could move it to the denominator. Now this is infinity over infinity. By L'Hopital, the limit as x approaches infinity, derivative of square root of x is 1 over twice square root of x. Derivative of e to the x is e to the x. If I clean that up algebraically, that's the limit as x approaches infinity of 1 over twice square root of x e to the x. As x approaches infinity in the denominator, I'll get infinity. 1 over infinity is 0. And that's the manipulation you have to do. I'm going to take the second problem. The limit as x approaches 0. Well, 0 squared is 0. And as x approaches 0, recall that the graph of natural log, as you approach 0, that's negative infinity. Now, positive or negative makes no difference. Whether it's positive infinity or negative infinity times 0, it's the same thing. The key, if you see an inverse trig function and you see a natural log, you never move natural logs. You have the option of saying this is the limit as x approaches 0 from the right of natural log of x divided by 1 over that, the reciprocal of x squared. Or you could say it's the limit as x approaches 0 of x squared divided by 1 over natural log of x. But we never move natural logs and we never move inverse trig functions. Now, the limit as x approaches 0, that's infinity. And 1 over 0 is infinity. Again, positive or negative makes no difference. L'Hopital applies, x approaches 0 from the right. Derivative of natural log of x is 1 over x. This is x to the negative 2. So that will be negative 2x to the negative 3. If I clean this up algebraically, that's the limit as x approaches 0 from the right of 1 over x divided by negative 2 over x cubed. This is a complex fraction. Multiply this by x squared top and bottom. Those cancel out. I'm looking at the limit as x approaches 0 from the right of x squared over negative 2. Or you could say that's 1 over x times x cubed over negative 2 multiplied by the reciprocal. It doesn't matter. As x approaches 0, that's 0. And that's pretty much how it works. So infinity times 0, I know what to do. How about these problems? This is infinity. As x approaches infinity, that will approach 0. Natural log of 1 is 0. So this is infinity times 0. And again, we don't touch logs. You should know that. So we take the limit as x approaches negative infinity of natural log of 1 minus 1 over x divided by, this is x over 1 divided by the reciprocal of that. And as you see, I could multiply by the reciprocal and get that back. Now, as x approaches infinity, that will be 0. Natural log of 1 is 0 and 1 over infinity is 0. L'Hopital apply. Limit as x approaches negative infinity. Derivative of a natural log of x is 1 over the argument times the derivative of this. This is 1 minus x to the negative 1. Bring the power down, positive. You'll get x to the negative 2, which is there. And derivative of x to the negative 1 is negative 1 over x squared. Those two cancel out. And I'm left with the limit as x approaches negative infinity of negative 1 divided by 1 plus 1 over x minus, not plus. As x approaches infinity, that will approach 0. You're left with negative 1 over 1, which is negative 1. Not that bad. Here, if I put a pi in there, sine of pi is 0. Cosecant of 3 pi is infinity. Here, there's an easy fix. And the fix is to make that simply the sine of 3x. And now if you put pi in there, sine of pi is 0, sine of 3 pi is 0. By L'Hopital, limit as x approaches pi from the left. Derivative of sine is cosine. Derivative of sine of 3x is 3 the cosine of 3x. when you put pi in there, you get cosine of pi, which is -1 over 3. Cosine of 3 pi is -1, and we get simply 1/3. Here we have the same issue. The limit as x approach, oops, that's not what I meant. I meant to move it. There we go. And here, that's approaching infinity, that's approaching 0, and tan of 0 is 0. I need to manipulate it. Well, I have a couple of options. I'm going to go with the option of leaving this out. When I move this to the bottom, that's the cotan of 1 over x. That's infinity. If tan is 0, cotan is infinity. By L'Hopital, again, you could leave the tangent up there and say that's 1 over radical x. Maybe I'll come back to that if this doesn't work. We'll see how that plays. Derivative of square root is 1 over twice the square root of x. Derivative of cotangent is negative cosecant of 1 over x times the derivative of 1 over x, which is -1 over x squared. If I clean this up a bit, I'm looking at the limit as x approaches infinity of positive. Now, this is a complex fraction. This is going to become, let's see, this is over x squared. So to make this all over the same denominator, let me write that in 2 steps. I'm going to move this up there. Actually, let me leave it down for now. I'm looking at 1 divided by twice square root of x over cosecant of 1 over x divided by x squared. The LCD for this problem is 2x squared. So here you multiply this by 2. You multiply by this by 2x to the 3/2. Not 2. There's no 2. It already has a 2. But if you multiply it by x to the 3/2, that becomes x squared. And you could ignore the denominators once that happens. So I'm looking at the limit as x approaches infinity of x to the 3/2. Instead of dividing by cosecant, I'm going to say that's the sine of 1 over x. As x approaches infinity, that's going to approach 0, but that didn't get me anywhere. Okay, well, this is what I'm going to do then. I'm going to go ahead and restart this problem, but do it backwards. Again, there are 2 options. You could do any of these problems. Now, inverse strict functions, inverse and natural log, you know exactly what to do. But here, I'm going to say this is the limit as x approaches infinity. I'm going to leave the tangent of 1 over x in there. Now this is x to the 1/2. If I move it to the denominator, that becomes x to the -1/2. As x approaches infinity, that will approach 0, that's 0. And 1 over infinity is 0 by L'Hopital's rule. Limit as x approaches infinity. So again, I'm doing this. And I'm writing that as x to the 1/2, moving up. Derivative of tangent is secant squared of 1 over x times -1 over x squared. Derivative of this is -1/2 x to the -3/2. Now, this is going to be the limit as x approaches infinity of, let me see. That's going to be the secant squared of 1 over x divided by x squared positive. I'm going to move this up, right? So that's going to become x to the 3/2 times 2. That is the limit as x approaches infinity of the secant squared of 1 over x. And this here is going to be a 2. 3/2, that's going to be square root of x. As x approaches infinity, that approaches 0. Secant of 0 is 1, because that's 1 over cosine. And this is going to be, as x approaches infinity, that's approaching infinity, so that's going to be 0 altogether. Now we get to a different problem. If you take the limit as x approaches infinity, that's infinity minus infinity. Well, we have a problem with that. Now we know exponential is growing faster than x. The answer is negative infinity, but we have to show it. Anytime that happens, you're going to factor out. If you see a fraction get a common denominator, if not, factor an x out. That will be 1 minus e to the x over x. Now, I'm going to go on the side and figure out what is the limit as x approaches infinity of e to the x over x. Well, that is infinity over infinity. By L'Hopital's, that's the limit as x approaches infinity of e to the x, derivative of e to the x is e to the x, derivative of x is 1. That's going to be infinity. So this is approaching infinity. 1 minus, and this is approaching infinity, right? That's what we got out of this. Now, isn't 1 minus infinity negative infinity? A very large number multiplied by a very small number will be negative infinity. And again, you need to show this work for this piece. And if I look at the next problem, we have the same issue here. This is the infinity minus infinity case. Well, infinity minus infinity, because secant of 0 is infinity minus infinity. Here we could just make it 1 over sine of x and get a common denominator, and most likely that does the trick. The common denominator is x sine of x. That's x minus sine of x. That's 0 divided by 0. I could use L'Hopital, limit as x approaches 0. The top will be 1 minus the cosine of x. The denominator of the product rule, derivative of the first times the second, plus the first times derivative of the second. If I let x equal 0, cosine of 0 is 1 minus 1, that's 0. 0 and 0. I'll use L'Hopital again. How many times can I use L'Hopital? As many times as it takes. Derivative of the top would be now the sine of x. Derivative of the denominator will be the cosine of x plus product rule. Derivative of the first times the second plus the first times derivative of the second. So it's going to be x minus x sine of x. If I let x equal 0, I'll get the sine of 0, which is 0 over 1 plus 1. 0 over 2 is simply 0. So again, I can only use L'Hopital if I have 0 to the 0, infinity to the infinity. Here's a problem. I put 0 in, I get 0, and 2 over 0 is infinity. Well, a power function, there's one way of manipulating a power function, and that is, I could write this as e to the natural log I could say that is the limit as x approaches 0 of e to the natural log of x to the 2 over x. Anytime you see a power, you're going to have to use logs. And we know that a to the log base a of x is simply x. We're going backwards. This will be limit as x approaches 0 of e. One of the properties of logs, I could move that in. Now I have two options. I'm thinking of this as either twice natural log of x over x or 2 over x times natural log of x, depending on what benefits me. If I look at it this way, as x approaches 0, that's infinity over 0, that's a problem. If I'm looking at it this way, 2 over 0 is infinity. Natural log of x is negative infinity. So if I multiply those out, I get negative infinity. And as the exponential grows to negative infinity, I'll get a 0. How about here? The same deal. If I put 0 in, I get 1 to the 1 over 0 infinity. Every time I have an exponential, a power, every time I see one of those cases, 1, 2, 3, 4, I'm going to say x equal e to the natural log of x. So when I see the limit and I see 1 to the infinity, I'm going to say that's going to equal the limit as x approaches 0 of e to the natural log of whatever that is. Because that's equal to the function itself. Limit as x approaches 0 e, and I could move that to the front, and that looks like 1 over x natural log of x plus 1. Again, algebraically, I could say that's 1 over x times natural log of x plus 1, or I could say that's natural log of x plus 1 divided by x. Here, I didn't use L'Hopital at all. But here, if I take the limit as x approaches 0, if I put a 0 there, natural log of 1 is 0 over 0. So this benefits me more. I'm going to think of it this way. Since that's 0 over 0, I'm going to apply L'Hopital and say the limit as x approaches 0, e to the derivative of the top is 1 divided by x plus 1 over derivative of x is 1. If you put x equals 0, you're going to get e to the 1. And that's pretty much what that limit is. Couple of more problems and I'm done. Now I will point something out at the end. I added a lot of problems because this section I don't think has enough problems. If I let x equals 0, I'll get negative infinity to the 0 power. Well, if I have a power function, I'm going to write this as the limit as x approaches 0 from the left, of e to natural log of whatever that is. And the reason we do that because property of logs allow you to move that to the front and you're no longer dealing with the power. And if I let x equal 0, I get 0 times. If you put a 0 there, you get infinity. So I'm going to manipulate that. As we mentioned, if you see a log or an exponent or an inverse strict function, you never move the log. That's natural log of 1 minus over. Instead of saying x times, you're going to put 1 over x. If you put 0 in there, you get infinity, and 1 over 0 is infinity. L'Hopital applies, limit as x approaches 0 from the left. Where did that one come from? Of e, derivative of the top is 1 divided by 1 minus 1 over x times the derivative of this, which is 1 over x squared. Derivative of 1 over x is negative 1 over x squared. Those cancel out. And I am left with the limit as x approaches 0 from the left, e to the negative 1 divided by 1 minus 1 over x. As x approaches 0, I'm looking at e to the negative. As x approaches 0, that right there is going to approach infinity, right? And 1 over infinity is 0, and that becomes a 1. One more to go. It's something I made up, again, because we don't have enough problems in this book. So I added 6 problems, I think. Here, I'll get 0 to the 0 power. Automatically, once I get a power function, I want to get rid of a power. Well, I use e to the natural log of the sine of x raised to the x. Properties of logs. I can move that up front. And now this is 0 times, and if this is 0, then natural log of 0 will be infinity. I need to manipulate that algebraically a bit more. Again, we don't touch logs, so that's going to be that's going to be e to the natural log of the sine of x divided by 1 over x. Now, if I let x approach 0, sine of 0 is 0, and this will be approaching infinity over infinity. I could apply L'Hopital. That's the limit as x approaches 0 from the left. E, derivative of natural log is 1 over the argument times the derivative of sine, which is cosine of x. And the derivative of 1 over negative 1 over x squared, that's the limit as x approaches 0 from the left, of e to the negative, and that's going to be x squared. Cosine over sine is the cotan of x. As x approaches 0, that's going to be, and I'm getting 0 times infinity again, so that's the limit as x approaches 0 from the left. And I'm going to rewrite that again as cotan of x. Actually, I could write it now as negative x squared. If I move that down, that's tangent of x. And this will be 0 divided by 0 by L'Hopital. The limit as x approaches 0 from the left of e to the derivative of this is negative 2x. Derivative of tangent is secant squared of x. That is the limit as x approaches 0 from the left of e to the negative 2x cosine of x. If I put 0 in there now, I get cosine of 0, which is 1, times 0, that's e to the 0, which is 1. Now, I do want to mention, if you go to the YouTube channel I have, and if you look at section 6.8 in second semester calculus, not OpenStax, second semester calculus, section 6.8, it is a lot more thorough than this. I have way more examples and I have more and more cases, but this is sufficient for this class. There's the homework, and that concludes this section.